Well, good afternoon, everybody. Thank you for coming and extending the automotive discussion. I was here for your talks earlier this afternoon. I think one of the pleasing parts of it for me as a technology journalist was that it was very concrete, very specific. It wasn't a lot of arm waving. You're actually clearly doing real work. But I wanted to start off very broadly, even though this might be a little duplicative, but I'd like to hear your thoughts from each of you. What do you think the single most promising application is for quantum computing in the automotive industry? And that can be, particular to your research, it's okay, but what is the most interesting or productive, fruitful avenue for the work? What do you guys think?
Well, I think the most promising application and killer application in automotive industry and for many industry in quantum computing will be material science. There we are expecting exponential speed up. And in automotive, it will really, now with the transition of the automotive to electrification, we are in urgent to find alternative material, cheaper, abundant, and solve a lot of problems for performance of the battery. And we need to have accurate tools to guide the experimentalist when we don't have an experimental data available. So these accurate tools currently on classical is very expensive and interactable. And here where I see quantum computing will really be a killer application. The other could be optimization as well. There we are expecting a polynomial speed up. But considering the applications and the scale we are operating at in industry, I think this is also optimization is another applications. However, I think more work needs to be done on optimization because we need to know what really are the killer applications in optimization that we cannot solve on classical, and we really need to use quantum devices to solve it. And there will be other applications like in long term, so those I see them as a midterm application. Long term could be cryptography because now with the technology in the cars, imagine if someone hack your car and you can have an accident and someone control your car, or quantum sensing. So these are another applications, but it's going to be in very long term.
And how about at BMW?
Yeah, I mean, I definitely do agree, right? Material science is definitely be that's most immediate application, and we can actually do something that we cannot do classically, so to speak, right? If we want to simulate chemical reaction on an electron sub-molecular level, we definitely need this kind of technology, and we can put all our classical HPC resources, everyone in the room, all the companies, every computer on the planet together, and we won't be able to simulate those kind of equations classically. So that's definitely the hope, right? And I mean, we touched on some of the topics we are looking into on a very high level, right? We already spoke about materials for the batteries, right? What kind of metals should go in the anode or the cathode of the battery. Similar for the hydrogen fuel cells, we are looking into similar materials there. So.
Okay, and what do you think? You talked a lot about optimization,
right.
and
so
I think that's very interesting.
I agree with them. So in my opinion, the most promising application is logistics, because the optimization, we need to solve large-scale size optimization problem. So it's quantum computer suits to solve this problem. Okay, thank you.
Yes, and Toyota.
I think material applications for some specific, very small area would be a promising application quantum computers. But I think so optimization is a promising area of quantum computer.
So that's interesting. So optimization and material science seem to be the heavy hitters for you all. To what extent are you expecting machine learning will apply? Because that's a subject, a technology I hear a lot about. Is that also applicable? Is that farther out? What do you think? Any of you?
I mean, it really depends, right? Machine learning is such a broad field, right? And just looking at the progress we made over the last couple of years, right? I mean, until 2012, right, we nearly didn't do anything machine learning, and now it's everything. It's vision, it's language, it's acoustic, it's basically everywhere. and it will definitely play also a very important role in making quantum computing happening, right? Because we do have issues like how does the data actually get into the quantum computer, right? We saw in our presentation that we're looking into training models that can capture complex data, so you can easily load that data into the quantum computer.
Pre-processing, basically.
Basically a pre-processing, but also the post-processing, right? When we want to integrate a quantum sensor with some kind of AI in order to get some state out of the quantum computer itself, right? We might have to rely on AI for that. Yeah, and needless to say, right? I mean, there are AI applications everywhere. There's nearly not a subject when you touch the car, when you touch a process where you don't have a machine learning component. So it will definitely have a big impact.
AI works on classical computers, obviously. What ways does a quantum computer give you some kind of speed up or advantage over classical AI ML?
Well, I think at this moment, it's still AI, ML, this is still very highly disruptive and fundamental research. I'm not so yet familiar so much with AI, ML, but I think one of the things maybe for when it comes for image, maybe this quantum Fourier transform might help to speed this process. Also, the differential equations that they have in the neural network, it could be also this one thing that can be also speed up because we have these differential equations can be solved faster on quantum computers. So this probably one of the things that can be done to speed up the machine learning.
At Toyota, Hirotoshi, I wondered if you could talk a little bit about what you spoke about earlier. Briefly, it seems you're using or expecting to use quantum computers for very detailed atomic level simulations. How good are they today? How good do you expect they will become for this very low-level physics research?
In my personal opinion, so nowadays machine learning plays an important role for material development, and currently, so we have quantum algorithms for chemistry computation. However, they are not for large scale, which we really need, but for high accuracy. But for machine learning data set, we don't need such a high accuracy. But we are currently DFT for the material development computation, but DFT works well for almost all systems, but for some specific systems, DFT fails. For such systems, quantum computing would have advantages.
So I wondered also if you wanted to comment on the NISQ question. So we're in the noisy intermediate scale quantum computing era, and that's obviously proved very fruitful for some early research and exploration of the industry. But are you expecting it will actually produce useful results at your companies?
So I think for NISQ era, we know that in order to, this is a noisy qubit. And the only killer applications in NISQ devices is if you can reformulate the problem in a very short circuit, get the results before the noise hits you. The problem is that in applications in industry, we deal with a large scale. So what is going to be killer applications there? I think still no one knows. It's still unclear if there will be advantage in industry or no. However, I think it's maybe to my opinion, the NISQ era only used to gain insights about the problem, know how to design algorithms on this hardware, get so much into the fundamental of the problems, and that will help us as this hardware matures. Then we know how to really use this hardware. We already know what are the problems that might take advantage of this quantum hardware, how we can design the algorithms for this. So that is where I see NISQ might just help us to gain insights. But at the moment, based on what we see, I don't just see some advantage at the moment at today.
So a critical tool to learn how to use the machines to develop the algorithms, but not necessarily actually useful until we get to
Until
fault tolerance.
maybe some breakthrough will come. The thing is that for noise, because of these noisy devices, if you use the error mitigations, then the problem is scaled exponentially with that, depending on what error mitigation you use. And then what is the advantage against classical algorithms? Need maybe better error mitigation methods. The technology is still really not mature yet. Maybe in a couple of years, some breakthrough will come. But as of today, still we don't see this.
Yeah, and we are, maybe add to that, right? We are still in the very early in this phase, in my opinion, right? But we have seen steady progress, right? Right now you can get like a 80 qubit Rigetti machine or a 127 qubit IBM machine, and the numbers are growing. And I'm pretty sure eventually we'll maybe be able to really squeeze out some value, some interesting signal within this algorithm out of those devices. The second point I would like to make is, right, it's obviously quantum is always only a small aspect of the entire user journey, right? When we talk about logistics application, AI applications, right, we need to think about the data, we need to think about end-to-end, very complex data pipelines, and the algorithm is a critical piece, but not the only piece, right? And while we are working on those advanced methods, right, it's also critical to enable the company or the entire automotive value chain to be ready when we get there. So, and that has typically also a very immediate value, even if it's only quantum inspired.
Again, to pave the way for the future. Yeah.
Okay, we need to prepare the era for the fault-tolerant quantum computer. So because we will have the problem to use quantum computer, that's the reason why we need to use NISQ-ADAS quantum computer.
I wonder how many of you are expecting that a fault-tolerant large-scale quantum computer really will happen? We've seen progress every year. It seems to get a little bit closer, but are you counting on it?
Absolutely.
No, honestly speaking, I don't know.
I don't know. I cannot. I think there are a lot of progresses coming, like people from photonic, like Ipsi Quantum, Aisin, and all. So they have roadmap to reach this fault-tolerant quantum computer. But we don't know of today. But they might. I think they all. This is their business. So I think we should have the hope.
So I wonder, what's your favorite kind of quantum computer? One of the interesting things as a journalist I see is there are so many different varieties compared to conventional computing, right? There are all sorts of different trapped ions and supercomputing, and we've seen the photonic designs now, and there's some other designs in the works, and neutral atoms. What particular architecture do you think is most practical today? And
difficult to say, right? I mean, because they are all not really delivering immediate value. I mean, obviously QEra, right? And we showed one example where we were thinking of, how can we apply this maximum independent set problem, right, to an automotive business application, right? And we came up with this autonomous driving use case in the plant, which yielded surprisingly interesting results at a surprising large scale, right? You can, for example, map up to 256 nodes on that machine, which is quite impressive, right? Is it perfect yet? Not, but it's definitely something that got us lately very excited, right? Because, hey, we haven't even thought of that kind of category of problem, and submitting that, right, to the cloud, and we got a result back, which was not just noise, was great. So,
do you think, how much harder is it to work with an analog quantum computer? They all look very difficult to work with from where I sit, but is that something that looks very difficult, intractable, or is it something that just needs a little bit of a learning curve and you're good to go?
So I have not personally used that one. I mean, obviously, DBIF, Anila, don't want to function somehow similar, right? So you have certain abstractions, in that case, right, like a graph, which is something at least a computer scientist or physicist or whomever is using that machine should be familiar as an abstraction to use with. So typically, I mean, and if you put something on AWS, right, you have sufficient blog posts, you have examples, so it's typically quite easy to get things going and to replicate certain type of experiments. Once you get deep into the matter, like with any topic in quantum computing, it can go quite deep, right, into the physics, and then you definitely want to have a PhD in physics or computer science or both.
Are they getting easier to use? Is the software, are the software tools getting better? I wonder if they're, I don't think we're at the stage of CAD software or something like that, that you can sort of just download a package and install it and run. How much easier are they to use today versus 2 years ago, for example?
Much better than 2 years ago.
How? What ways have they improved?
So we can use the cloud service. So it's easier than before.
You don't have any desire to run your own quantum computer?
Okay, so we have the QCB Forge, so it's easy to use.
Nowadays, we don't need to consider architectures. Software automatically optimize our circuit for each architecture. Yeah, so it's very so we can easily use current quantum devices.
I can just add, I think there's now a lot of open sources, so that allow you to play with and also to test. And so I think nowadays there are like Qiskit, Pennyland, and many really. And now even universities are having their open source, so and it's available for free. So I think everyone now has a lot of, like, have really chances to download and use and test. Even IBM allow people to access some quantum hardware, so you can download these open sources, play with, and submit jobs and practice.
How is the, oh, sorry.
Yeah, and maybe adding to that, right? I mean, the abstractions are gradually moving higher, right? And we do have, specialized abstractions for quantum machine learning and Pennyland, Qiskit and stuff, all good works. But in my opinion, we are probably not at a level yet where a domain scientist or an engineer, right, can use the machine and really just focus on, oh, I have my computer fluid dynamic simulation and I just need to press run and get a result. We are definitely not at the level that the domain business analyst engineer can use the software. But a computer scientist, right, who knows how to run jobs, I mean, definitely will be able to replicate the examples, right? So.
How is the talent pipeline looking with work at the university? BMW is endowing chairs, and we have, IBM is letting students use it for free. Is it getting any easier to hire graduate students?
No. I mean, that's obviously one, not the only motivation, right? But we are endowing those shares in order to kind of have a fresh pool of talent coming in, and I guess we need to raise the quantum native generation of physicists and computer scientists who grow up with that and kind of, are being able to take the stuff that's going on right now to the next level. And yes, I mean, the talent pipeline is tough, right? So.
Yeah.
I wonder, we've heard some news at this show about error suppression from Kedma and from, with FireOpal from Q-Control. What do you guys think about, obviously the qubits are noisy, but what do you think about error suppression? Is that providing a meaningful advantage to over what you've been able to use in the past, or have you been able to even try those technologies yet?
No.
I mean, the error suppression is probably not quite end user ready yet. I mean, those are basically experiments that they do and say, hey, we build a logical qubit, right? We use multiple physical qubits, and the error rate we now get is better than the error rate if I just use one single physical qubit. But I'm still getting a significant high error, right? And the issue is the machines you can actually test that don't have that many physical qubits, right? Mm-hmm. So it's kind of either you run the error correction or you run an application, but you don't run both.
Yeah, because there are different things. There is the error correction and suppression. This is work on fault-tolerant quantum computer where you need million of physical qubits to run. And there is, in NESC, we have error mitigation methods. So those methods that about suppression of errors, this requires a lot of qubits that we don't have today yet.
Yeah, it seemed like the discussion was maybe you get 3 orders of magnitude improvement. It doesn't get anywhere near, obviously it's a different approach than fault tolerance where you're correcting errors, but It seems like it could potentially make NISQ computers significantly more useful, deeper circuits perhaps, but I guess if it's still too green to really...
No, so the path to a fault-tolerant quantum computer will be via error correction, right? We need to have perfect qubits that have a certain kind of, high gate fidelity, right? And 99.999, whatever, high error rate, right? And then you need to put the error correction on top of that. But in order to do so, you need to have many qubits, and not only that, you need to have also a very long coherence time, because you need to, if you detect an error, right, you need to kind of correct it. So it's basically the path toward a fault-tolerant quantum computer will be via error correction. So.
What's the biggest difficulty for you technologically? What's is it the noise? Is it circuit depth? What specifically would you like to see improved most to make your research work better?
I think it all. So we need more qubits to be able to run useful applications in industry. We also, to have those large number of qubits, we also need to solve the problem of noise. We also need to improve the fidelity of 2-qubit gates. So there's things need to be done for the measurement. So I think they're all everywhere, and also we need still to develop better algorithms probably also.
Mm-hmm. Any other thoughts over there?
I agree with her. So we need some more qubits and high fidelity quantum computer.
Currently, we are discussing number of qubit and depth, but I think we have to discuss operational time. For example, gate operational time, state preparation, and readout. I think it's a big problem to be solved.
Mm-hmm. I wonder, I see a lot of progress at the low level in the hardware. Do you feel that there needs to be more progress at the high level with algorithms too? We don't really have that many quantum computing algorithms, and perhaps if there were more, then the quantum computers could tackle a wider range of problems. Would you like to see more algorithms? Any particular areas where you think that could significantly improve the capability of a quantum computer?
Well, for quantum algorithms, it's there is less quantum algorithms we know, and that's because it's very hard to develop them. So since we know about quantum algorithms, like there is a quantum computing since 1980, when Richard Feldman said that, then we have the sure algorithms and Grover and quantum phase in 1994, 1995, 6, and it takes many, many years to come up with those algorithms. It's just not easy, and I think that's why we need to have those NISQ era, because it might help us to get insights on, like, learn how to design those algorithms. It's just they are so difficult.
We definitely need more algorithms, but currently we're really limited by the hardware, right? To give you one example, deep learning. Right now, the whole world is running on deep learning, right? But Rosenblatt invented the perceptron, right? So basically a neural network with a single node back in the 50s, right? It was not viable. Yes, you were able to run it on a computer back then, but you were not able to do something meaningful with that, right? And it took like half a century in order to get to a level that you can actually do that, right? And a lot of algorithm research, yes, there's a lot of great stuff happening in theoretical computer science, which gives us, upper and lower bounds for certain types of, algorithms. But a lot of computer science research, and in particular in AI, is basically empirical. So you need to run stuff at a large scale on a real machine and then push the limits forward, right? So, right on Moore's law. So.
Any other algorithm desires?
Yeah, machine learning, for example, neural networks needs iteration to run. So we need high fidelity and low noise machine.
So speaking of AI, there was an unpleasant long AI winter for most of the last century. Now it's on fire. Everybody's using it for everything. That's a remarkable change. There's some people who worry about a quantum winter, and I wonder, do you all worry about a quantum winter, some period where the progress slows down and the enthusiasm cools and the companies stop investing in the technology? Is it a worry or not?
For us, for automotive, we are not a quantum computing industry. I mean, no, like we are not just our industry just in quantum computing. We are an automotive. We are trying to find applications and take advantage of the quantum computer. So for us, we know that it will take time. We need to identify use cases. So we focus on our research. It's now just, I think, what happens because of this is just we have a lot of problems. And we just need to focus how to really design the algorithms. It would take time. It's not going to be solved today. So I think in science, we always know there is this time that we don't have results, things doesn't go well. So it's just going to be a matter of time. But I think we are not worried that much. We just focus on our problems and we try to find a solution.
So you have some patience.
I think I watched a video for Professor Pinfringa. He is a Nobel Prize laureate, and he was saying actually in his videos, like if you want to be a scientist, you have to stand for the disappointment and and you have to be patient.
Yes.
Yeah, I mean, I do agree. I am definitely not afraid of a winter, and the opposite. I love winter, right? You can go skiing, you can do fun stuff out there. It's a bit quieter, right, than the spring where you, I need to change the world, right? Everything is blooming. And obviously it's great that exciting is in the ecosystem, but at some point, in particular, if you are the end user of those technologies, it would be helpful, right, to get some clarity into the market, right, and see, what's working and what's not working. See beyond the hype, and at the end of the day, right, there's Amara's law, right? We always overestimate the impact of the technology in the short term and underestimate it in the long term, right? And everyone is aware of that. That's also not a new law, right? And we just need to work through the emerging technologies to its maturity.
I'm worried about that. So Google showed the quantum supremacy before. So, but now we don't have the research paper, the quantum supremacy in industry.
Yeah, I think the winter will come. So it strongly depends on whether we can find practically useful application or not.
So you mentioned Amara's law. There's also Moore's law, which has come under a lot of pressure recently. There's still progress with classical computers, but each year it seems like the cost per transistor gets higher. Only the premium people can afford the newest processes. And a lot of the quantum computing people I've spoken with are part of the HPC, the high performance computing world, where progress is slower and it's slowing down and getting more expensive. Does that make it easier to invest resources in quantum computing? Does it make it easier to make the case to the high executives at the company that you need this kind of a program?
It's definitely one of the motivations, right? We need to look for other ways to scale certain types of workloads. We are probably not at the entire end of Moore's laws and they're not scaling, so there's definitely a lot of things that can come. Right now we have to just scale in different ways, also on classical semiconductor technologies, be a bit more application specific, right? Optimizing for our AI workloads. And certainly, right, I mean, quantum computing will be an accelerator for certain types of specific workloads, but it will not be a catch-all for everything, right, until it runs on your smartphone. Definitely some time to come.
Yeah, we have this strategy also for like we have this researches we can deliver some near value when we use the classical computer HPC, but we are also investing on this quantum computers to solve some hard problem, and we see where the value will be. So we also need to invest in there. So making some kind of balance, investing in near-term applications, but also somehow for what's coming in future.
And I think many people see it as ultimately as a hybrid technology in any case, where you have some quantum accelerators on one side of the shop and classical on the other side, or the cloud, as it might be.
No, to add to that, right, I mean, IBM put out this vision on quantum-centric high-performance computing, right? We maybe have many QPUs which are small scale, right, which are in the beginning connected by classical networks, in the future connected by quantum networks. And at the end, a lot of the HPC methods for parallelizing applications, for programming those will apply to the quantum computer, right?
So I wanted to get, if possible, a concrete example of the improvement that's possible. Some research you can do on classical computers. It's slower, more expensive, but they're the breakthrough examples. And I thought the optimization question was very interesting. You had some examples of just how complicated the logistics network is for your company. And can you just give an illustration of how the magnitude of that computing challenge that you hope you'll eventually be able to tackle with all the different, the plants and the logistics warehouses and the trucks and the how many, tons of products shipped per day?
So I want to make sure, so say again, please.
Oh, I'm just looking for, if you could be specific about how you think quantum computing could address your extreme logistics challenge, because you had a very specific layout of all the difficult shipping that you have to do every day with all the different trucks.
Yes. So that's a good question to answer. Sorry, so it's hard to answer.
That's okay. Well, that's fine. We'll move on. I also was curious specifically about, I was listening to the aerospace discussion, and there was a lot of talk about computational fluid dynamics, CFD, and perhaps that's an area you're interested in as well. I'm not sure, with a lot of aerodynamics challenges, perhaps structural challenges. How would that apply in the automotive industry?
Yeah, definitely.
Okay. Well, in automotive industry, so there is the fluid dynamics, but I think what is really behind these things is the main problem is to solve this differential equation. So because this is all how things move. And that is not just gonna be for fluid dynamic is one of them. So, and we know in quantum computing, there's these algorithms that can solve this differential equation faster than what we have on classical computers. So this will speed up calculations for this. It can also work for problems, also not just for fluid dynamics, but also for battery things on the system level. So it will, it's definitely one of the potential applications in automotive.
Yeah, I do agree, right, 100%. I mean, we briefly touched on that in the presentation. We have an HPC infrastructure, right? I mean, 80% of the stuff we're running there is aerodynamics and crash simulations. We have HHL as one of the algorithms, right, that promises exponential speed up for solving linear equations, right? When you have your partial differential equation, you need to discretize it. You end up with a lot of linear equations, and you need to solve them. I mean, there are many challenges, right? For example, getting the data out, but it's definitely one of those compute-intensive problems where a fault-tolerant quantum computer will provide a speed up. And we also had like a very good example. We actually published a blog post with AWS yesterday, and I know now the expo hall already closed, but together with Pascal, we basically took the Navier-Stokes equation on a very, very small scale, right, on the wing of a car, and kind of showed a variational algorithm, DQC, that Pascal developed, and showed that you can apply it to those types of aerodynamics problems. So very impressive.
Okay, so we are interested in the fluid dynamics. So high performance computer can solve the fluid dynamics problem in our company. So now we are interested in the big data analysis by using optimization or machine learning method.
Yeah, CFD plays a major role in automotive development. For example, for fuel efficient body shape with good aerodynamics, and also used in engine combustion optimization. And we also use it door mirror shape optimization without wind noise. But so actually, I'm not working on it, but we are very interested in it.
I hear a lot about, for many years now, the battery example, better batteries, also lower cost fertilizer manufacturing and better solar cells. These are examples that come up over and over and over in the materials science domain for quantum computing. Is that real? Is that, can you actually improve that, or is that just good marketing to get the journalist to write the story? Batteries, real or not?
I think you mean real for simulating it on quantum computing?
Yeah, exactly. Can quantum computers really solve that problem to deliver better battery chemistry?
It will definitely help, but I think not just alone the quantum computing. I think it's a combination of machine learning and quantum computing, because machine learning will help to scan all this material, give us some suggestion of some materials, and then that is where we can, in quantum computing, we can take these materials, then really without having any experimental data, we can really try to find out what are the best candidates. So in battery, we really have many issues. We need to find alternative materials, especially for cathode. We have issues because of the shortage of this metal like nickel and cobalt. We need to find alternative material. We also know that the battery cost is very expensive. We need to find alternative materials that are cheaper. Performance of the battery, charge rate, and driving distance. So we know, like for example, we know that if we use a solid state battery, we know that will dramatically improve the driving distance and safety of the battery. But we don't know what's the best solid electrolyte. So this is maybe where places that we can use quantum computing to find this solid electrolyte or solve the problem of reactions happen at the interface between electrolyte and electrode. So definitely yes, and also think about innovation even for having a solar cell that you might cover your car with solar cell to like charge your battery when you are driving. So there are also a very interesting material in organics that are called singlet fissions, and we know that we cannot simulate this on classical computers. So this is another material that where we can, quantum might help there. And I think for material, it might really make some like it would help to really make innovation in materials and move this battery. But I have to say that that's not possible today.
We have to wait for fault-tolerant machines?
Yes.
One last question. Where do you think the quantum computing hype is worst? I know there's a lot of real progress, but is there something that irritates you, somebody, some technology that's overpromised here? Nope, nobody wants to.
No, I mean, there's certainly a sufficient amount of hype everywhere, right? I mean, optimization was like, the first type of quantum hype, right? Back in the late 10s, 2017, 2018 with the D-Wave machine, right? Everyone was looking for optimization problems, right? Because that machine used that, solves those kind of problems, right? And with every technological advance, where you demonstrate something on a very small scale, people get excited, no matter whether it's, generative AI, whether it's now maximum independent set problems on the QR machine, people get excited, right? Because we have progress there and we want to get behind that. And very likely there might be a minor disappointment, right? Because obviously we are still on a scale that is not business relevant, no matter whether it's battery or whether it's numerical simulation, whether it's optimization.
But it's real.
But it's real, and that gets excited, right? It actually works. Even if it works only on a very small scale, it works, and that's awesome.
All right, well, thank you all for your ideas and your comments. I really appreciate it.